I want you to think about the following problem. Suppose that you wanted to take a strip of paper and without using a compass or a straight edge, which we know how to make an equilateral triangle. Okay, now you all know how to make an equilateral triangle with a compass and a straight edge, right? Okay. Well, how about this as a new method? So I take my piece of paper, okay, and well, I'm not going to use a protractor or anything. I'm just going, and I'm not even going to estimate. I'm just going to make a crease. Okay, so I make a crease. I don't even care how I make it. I just make a stupid crease. Okay, you do that too. Make a crease. Okay, crease down. So pick up the left, fold it down, make a crease. Then take the right side and fold down along the crease. Okay, as perfectly as you can do it. So, okay, so step one, make an arbitrary crease, unfold. Step two, take the right side of the paper and fold down so that it's along that crease you made. And if you've done it properly, you now have two creases. Okay, you made a triangle, all right? Okay, then what I want you to do is at this point, you're going to alternate. You're going to fold up. So fold up against the crease you made. Fold up as perfectly as you can. Fold up. And then fold down. Here's the code. So you do two downs, and then you follow it by up, down, up, down. Just do a few up, downs, up, downs. What you should discover is you'll have equilateral triangles. Or they should look like equilateral triangles. Okay? So here's the question. Are they equilateral? If so, why? If they're not equilateral, why do they look equilateral? Those are the questions. If you have some ideas, share them now. Otherwise, I want you to share with your partner and start working it out. I want to give you a hint. Okay? What I've noticed in the past few weeks doing geometry with you is that most of you, myself included, tend to be I'll keep the paper for now. Most of you tend to be a little scared of thinking geometrically because you'd rather think algebraically, okay? And so I chose this activity out of kindness, okay? So think algebraically. Do you see any angles in this picture? Well, you have to label them.
Pencil.
Well, you want to determine if you have an equilateral triangle, right? So you want to see if you can get a 60-degree angle. Well, you're going to need to do a little algebra. So think about it like this. Everything is determined by what? What determines the final structure? So I make a decision, and then after that, everything's automatic. What's the only decision I made in my folding?
Folding it against the crease.
What?
Folding it against the crease.
But which crease?
The crease you just made.
The first one.
The first crease is my only decision. Okay. So it's an algebra problem where you have a variable. How do we interpret that variable? Any suggestions? X. What's x? Come to the board with an x.
I didn't say that.
No,
that wasn't me.
It wasn't. Who said x?
You, no worries. It's a ghost, I guess.
Get to the board, someone.
I'll call this A.
You call that a, and now why is that equal to a?
Parallel lines across right here.
Ah, okay.
Alternate.
Good. Okay, so that's also a. Good. All right. So, right? Because after all, it's not just any old piece of paper, it's a rectangular strip of paper. Why don't you now start working at your boards and see if you can generate some other equations. So if we call this, remember, this is completely arbitrary, right? This angle could be anything. This is A, this is A. So now the question is, what's this? What's this? What's this? What's this? Think about it. How do we get these angles here? Is there anything you can say about these angles? Use your piece of paper to help you out. Use some more paper if you need it. I want to get generate some ideas. If you need some more blank paper, I think Jasper and Gabby have some.
$1.
So if we have this is 60. So only 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13. And this would be considered this one.
That's right.
And this would be considered this. So
And then,
this,
we know that this angle would be equal to that one for sure. But we don't know anything about that center one though, right?
Yeah.
Or do we? That's the question. What do you know about that center one? Because think about how it was made, okay? Use the piece of paper to think. There is a relationship between this angle and the other angles, and it's a pretty simple one if you think about it. You might want to look at these pictures here and see. Because you're doing folding. What does paper folding induce with angles?
It's a tetrahedron. Actually, no, it's a
That's an octahedron.
octahedron.
Yeah?
It's close.
So you started out with, you had this fold,
Uh-huh.
and when you made another fold, it was coming from the
Uh-huh.
stop area, and it kind of copied
Uh-huh.
this. So you know that when you bring it back down, these two were congruent.
Uh-huh.
So since you know this angle,
Mm-hmm.
and according to alternate interior angles, this is the same as it.
Uh-huh.
According to this is an isosceles triangle. So
What's
this,
an isosceles? How do you know that's an isosceles
Because
triangle?
two sides are congruent.
How do you know they're congruent?
Oh, because one was folded on top of the. I don't know.
Is that true?
No, that's not
It's
true.
how is it not true?
Because you fold like this.
Yeah.
This
Here's a
folded-
counterexample for you.
So this is a trapezoid actually.
Here's a counterexample. That's not an isosceles triangle. What you need to be struggling with is what happens angularly when you fold? What is going on when you do this fold? What's happening? It's paper folding. You've been folding paper since you were 3 years old. How many of you do origami?
I do.
How many of you wish you could do origami, but you're too clumsy? Okay. See? Oh, yeah, look, there's, yeah. But anyway, paper folding is very, very simple. There's a very simple thing that's going on with paper folding. What geometric transformation is going on when I transform this into that? I am transforming the right side of this piece of paper, and suddenly it appears over here. Would you, if you were going to categorize this as a geometric transformation, would you call it a translation, a rotation, or a reflection?
Flippation. Yeah, flippation.
No.
What?
Flippation. No.
Rotation?
No flip.
A flip, in other words, a reflection.
Yeah.
Okay? A reflection requires a reflector.
Yeah.
You reflect about a line. So
But then the line is.
where does this point go when you reflect it about the line?
In the middle.
It stays where it
stays
is.
there.
And you can see that that makes sense because this line
The line
stays
is-
where it is under reflection. Where does this go? It's going to go to its reflection. Let's see if it really does. So this should go to sort of over to there. Did it?
Yes.
Yes. How do you define that? So for example, if this point, if this point is going to be reflected, how would you do it with compass and straight edge? Or how would you actually make it happen? What do we need to do? Where is the image point going to be? When under that reflection, where would it end up going? Let's get some colored chalk. I hear the word perpendicular. So you draw a perpendicular to the line, and so this length here should be that length there. And that's the image, right? Okay? So let's apply the same idea. So this crease here, it's the image of what? Let's do some labeling. Let's call this a x, this point x, this point y, that point is z, and that point there is w, and this point I'll call it p. Okay? What's going to form zp? ZP is, so what we know is that when we do the fold, we're really reflecting about the line ZW, okay? What ends up being ZP? What is ZP? What's the pre-image of ZP? What's the mother of ZP?
AW. Yeah, AW. I mean ZW.
ZW,
Yeah,
are you sure?
100%.
Then you fold it, right?
ZY. ZW is one of those freaks that is its own mother. Because we're folding about ZW. Let's make the diagram a little better. You know what? Let's use a lowercase, or let's use a Greek letter to distinguish it from the points that are Roman. Choose your Greek letter since it was your idea. Beta. Beta is one of the prettiest, so that's a good choice. Okay, so beta. Okay, even when I draw beta, it looks good. Okay? All right, so the point is, when we actually do the folding, what we're doing is we're performing a reflection about the line ZW. Okay? All right, so the image of ZW is itself, because when you reflect on a line, the line stays the same. Where does YZ go? Where does Z go?
Stays there.
Stays the same, right? So where does Y go?
Y goes to P.
Y goes to P. That's how it was built, right? So when you do that, when we did that first fold, where's my first fold? When I do my very first fold, you can actually see it happen here. This thing here is going to go, uh-oh, it didn't work. What happened? It didn't go there, did it? No. Okay, so let's think some more. Let's make that second crease happen. So here's my first fold, okay? Then to make the second crease happen, I reflected about something else. Okay? What did I reflect about? I reflected about this line. Where did that line come from? It did come from the other side, but where did it come from? What's going on now? It looked so good. It looked like this should be that, didn't it? But you can see it wasn't. Right? See? So the second fold was here. So think about what's happening. How, once we have this line drawn, this crease is already predetermined. What is its geometric relationship to this angle? What is this crease? Think about it. This line here will move to this line. Okay? Do you see any congruences? I can't hear you, Jonathan.
Isn't it 180 minus A over 2? And I'll give you...
Isn't you mean beta?
Yeah, 180 minus B over 2.
You're saying this is 180 minus, like that?
No, the whole thing over 2.
Ah, 180 minus beta over 2. Why?
Because when you fold it in half, you're folding one whole obtuse angle in half. So then it's
In half?
Yeah.
So more specifically, what is ZP?
ZP.
What does ZP do? Let's add one more point of reference. Let's call this Q.
So ZP is the angle bisector of QZB.
Exactly. ZP bisects angle QZW. QZW. Okay. Let's see why that makes sense. What's being done physically? What's being done physically is you are taking this piece of paper, you're folding it along some mystery line in such a way that this line ends up coinciding with
GW.
this line here. It's folded along ZP, so it's not going to coincide with ZP. It's going to coincide with ZW, right? Okay. So it's going to coincide with ZW. And so just look at the picture here. Focus on this angle. I know it's hard to see here, right? Focus on this angle. When I fold over, I have the same angle, but it's been doubled up. This angle and that angle have to be the same, right? This line here is going to flip over to this line, okay? So this angle here has to equal that angle.